BHEL. And that time I was working in turbo machinery group, but I also did coal-fired combustion. So we had a combustion plant, furnaces and all. So I started my CFD journey with actually CFX4 and CFX5 for combustion. Then also our group mainly used the task flow also. I did not use too much, but I know about task flow very well. So this is how I started. Then I started to work in Sumitomo Rubbers in Kobe, Japan from year 2004 and till 2012. And that was the time when I started writing CFD softwares. So I had one open source code that time, single region unstructured grid. And then I also had a LES DNS code for Sumitomo that we used to simulate golf ball and other things. And this LES DNS code was a code where we could solve very fine meshes like 3 billion, 4 billion, and we try to go as close to DNS as possible for golf ball. And then having so much experience writing the CFD software at that time, I was hired by CDA in 2012 to be a developer for Star CCM. And in Star CCM, the flow model is what I worked on. So segregated flow model was my area, and dispersed multiphase actually. So, but mainly flow. And then in year 2015, I started developing Wildkatze. I came out of CDA and I started to write my own multiphysics software. So this is how Wildkatze come about. And now Wildkatze is basically 11 years. So we are also developing WKNext, which is the next generation. So we learn something from Wildkatze and we go to next generation, which is a little bit more advanced. So as I mentioned, Wildkatze started in 2015. And idea was to have a software that is for industry, because that time if you did not use Fluent or Star CCM, then mainly you use OpenFOAM. And OpenFOAM being not so stable was difficult to be used in industry. So the idea was to create a software for industry that is very stable and also accurate, and not focus on the academic side of it. So basically we are not interested in solving simple test problems that you can publish, but we are more interested in solving the problem for clients or companies, because they really in the end need calculations that are very difficult to be done. So, and the framework was such a way that it should be easier to develop for them. So that is something for the developers, but it should be flexible enough that if somebody want to do advanced research, they can do. So we should start with the question why Wildkatze. Basically, there are many other options, like you have commercial softwares, then you have open source. Now many more open source are there. So why Wildkatze would make sense for you? So if you are a commercial software user, CFX, Fluent, etc., then maybe you should look at Wildkatze as a cheaper alternative, even though we are usually more accurate than them. So if you make a test, you will see in the presentation also that whenever we do validation, usually we are more accurate. So that's accuracy is one reason why you can go, but we are more robust. So Wildkatze at the moment is the most robust CFD code. You can have a very bad meshes, anything, or very difficult calculations. It does allow you much more advanced user coding. So if you are a Fluent user or Star CCM user and you want a very low level access to the software, then you will not be able to get it. So the software Wildkatze does allow you. So if you are coming from Star CD, where you are used to access the mesh and do things with it, and now suddenly Star CD is not being supported and you are frustrated, maybe Wildkatze actually we allow much more access to the framework than Star CD. Then you can just use it as a finite volume framework. So if you are in research, let's say you're doing master's or PhD, and you want to develop your own model and you want a framework, you don't want to write everything from the scratch, then your option is to only use OpenFOAM. But you can use this also as a finite volume framework and do your thing. You don't have to use any model provided by the software. You can just use user transport model and you'll be okay. Or in the last scenario, when the project is too difficult. Let's say you are running with the commercial softwares, but you are not able to get the results out, you're frustrated, then maybe the software makes sense, because so far 90% of the projects that we have done, they are like that. The client has been trying with every software, not able to get any results, then they try with the software and they have better luck. So then comparison with open source. So basically, lot of advanced things that Wildkatze come up with, you can do with open source also, because you can compile the code. But usually what happens when you are in open source like OpenFOAM or something, you cannot simply easily do things. For example, if it is a multi-region or multi-phase, it can get very difficult very fast. So that's why there are open source alternatives, but in this one, you will do it with much more ease. So all the other things do exist here that you can compare with other commercial software, and we are obviously many times more accurate. You will see this thing as I present further. So where do we use Wildkatze so far? Wildkatze is actually very, very advanced software. Even though in this presentation, I will not be presenting everything, but it's extremely advanced. In fact, if you look at the only solver framework, probably this is the most advanced one. So where we have been using, so all these black areas, like flow, turbulence, multiphase, aerodynamics, acoustics, conjugated heat transfer, and non-returning. Here we have done a lot of projects already. So we know the software is very robust and very accurate. In the case of reactive flow and combustion, we have not done any serious commercial projects. And we do have electromagnetism in plasma. We can do MSD also. But I would put them in a gray category, because software is, you can say, okay, it does not have too much experience doing. But other areas, we've been doing a lot of projects for last 10 years. And we have compared the software also many, many times. So in Wildkatze, as I came out of CD Adapco, one of the things was that I wanted to create or do innovative things. So we don't want to just be stuck in second order finite volume solver. We wanted to do something better. Okay. So otherwise, there is no point of me writing this software. If we are not doing anything better than what is already available, then why to spend so much time? So one of the, wait a second. So one of the innovation that has come out of it is we have a higher order simple method. Now, higher order methods, there is a lot of research going on in finite volume, finite element, etc. And usually when you see finite volume higher order method, all of them usually they fall into one category of flux-based method. That means they calculate the higher order fluxes, integrate, and typically they are more explicit in nature, and the time step is limited by speed of sound and typical Riemann type of solvers. But in industry, we use simple method the most, the pressure-based method. So to my knowledge, in finite volume, Wildkatze is the only simple-based method. And here, what do you see? So just to show how effective higher order method can be, we create a solution from a benchmark mesh that you see on the top right corner, which is very fine mesh. And then our idea is to reproduce the result with a very coarse mesh. So you can see there is a huge difference between the mesh sizes. And what we are seeing is that there is a band pipe And the flow, it's very difficult to simulate this type of configuration. And we prop on a line, which is a red line here, the left bottom, and we plot a velocity on it and see what happens. So as you can see, the second order method is far away from what the profile should be from a benchmark profile. But even on a very coarse tech mesh, you can get a very good results out with a higher order. And typically, higher order method in Wildkatze are 40% or so additional cost. So basically, if you are taking, let's say, 10-second simulation in a second order method, you will be take 14 seconds. So not so expensive. Typically, if you go to finite element solvers, when you increase the go to higher order, it adds a lot of degree of freedom. That means the cost for solution also increases quite a lot. So it kind of defeats the purpose. But here we tried that it's not that much additional cost. Plus, what we see is that we try to work, as I said, the solver is for industry. So I try to make sure that the solver have a higher order accuracy even on unstructured meshes. Not like you don't need to have very, very good meshes, and otherwise you will not get higher order accuracy. It's not like that. We have been testing them on general polyhedrals and what. So it's deliberately I'm trying to show you on a tetrahedral mesh and not a hexa mesh, which would be kind of like cheating. So second example of a higher order accuracy would be the result coming from this paper. This is a very well studied problem. Taylor-Green vortex decay at Reynolds number of 1600. And this is well studied. You have many published results outside. And what do you see here is that the results we have taken from this paper that I will show on the utility of GPU accelerated higher order method. Here in this paper, they compare star CCM with finite element DG code on higher order. Now, the star CCM is run on 256 into 256 into 256 match. The reason why they have run it like that is that when you go to higher order in finite element, as I just mentioned, the degree of freedom will go up. So even though the mesh was coarser, the degree of freedom in finite element were 256 into 256 into 256. So star CCM also was run on that. And you can see that the second order method is in the star CCM is away, but the third order muscle. But same case, we run with Wildkatze is 120 into 120 into 120, and 160 into 160 into 160. So we are considerably coarse mesh than star CCM. But still, the higher order solver does a very good job. Now, in this case, you see the star CCM is run on a very fine mesh. It's a nearly semi-DNS mesh, because for this calculation, the DNS results are produced from 512 into 512. So basically, they are not far away from the DNS type of thing. So it's defeat the purpose. You want to use a higher order solver to save the cost. So typically, you should not be going above 160. So what we did is that we run the star CCM ourselves. And also we can compare, given the same mesh. So in this case, I think the mesh is 160 into 160 into 160. And we are comparing star CCM. We are comparing muscle scheme in star CCM with special settings that are suggested by developers of star CCM. And also we are comparing the third order formulation of Nishikawa-san. So recently, if you see, a lot of publications are done by Nishikawa-san about higher order in NASA. And so he suggests one cheaper way of doing higher order, so we use that part. So what you are seeing is that higher order Wildkatze is red, and third order Nishikawa is yellow. The only difference between them is the phase interpolation is done by the scheme that suggested by Nishikawa-san. So everything else is same. So just if you go to what he suggests, you already lose a lot of accuracy. So there is no free lunch. Then you see the second order upwind star CCM results. I will point out that Wildkatze second order upwind scheme results exactly fall on this line. So star CCM and Wildkatze in this case produce identical results. There is no difference between these two curves. Okay, so I did not plot it here, but just know that if you are curious how Wildkatze would have done with the second order upwind, then the curve fall on star CCM. Exactly, there is no difference. You cannot. That's why it's not plotted here, because it doesn't look different at all. The muscle scheme in star CCM with settings that a developer suggested, that is basically trying to take out the limiters, does better, but you can see higher order method in Wildkatze is far better. Yeah. So yeah. Now, second innovation that came out of Wildkatze is that we have a better scheme for the BOF. Now, when you are doing volume fluid calculation and doing the multiphase calculation, the interface capturing scheme matters a lot. So we developed a completely new scheme for the interface capturing. It's nothing like anything that you see in other softwares. And the original formulation actually does not even have Courant number inside. So in theory, at least it is a Courant number free. And it's very sharp. So if you are using isoid vector, etc. in OpenFOAM or geometric scheme in Fluent, this scheme is pretty much sharp as well. So the core concept I can tell you, so that if you are curious, because it's completely different. So the idea here is that when the interface moves by delta t time, so imagine that the interface is there and you take a step in the solver, it moves by delta t. The idea is that the interface is sharp even after that dt is taken. So this way of thinking is a little different than how typically done. And typically, you try to estimate the interface and then you solve the linear system or affect the interface. But here we assume that interface is going to be sharp. So this is built in the assumption. And from this sharp interface, it can be estimated by some sharp profile, maybe a polynomial in 3D, or I am using the think scheme, which is a hyperbola scheme, and it's kind of looks like a left bottom interface style. So based on certain parameter, it can show the sharpness of the interface. And then I can calculate the gradient limiter. So in this case, you can see that if beta is 0, then you are first order upwind. And when the beta is 1, it's second order upwind. And when the beta is 2, it's a fully compressible scheme. So a typical compressible scheme for the algebraic sense will be beta between 1 and 2. So we estimate this beta from a given profile, and that's the innovation part. So, and then we blend it with a lower order scheme based on the interface pattern. So how does this scheme do? So we take a very difficult test problem for it. And this problem, you can see that we are advecting the disk from the left to right on a 45 degree. So it's a Cartesian mesh, you will advect it, and after 4 seconds we see. And what do you see is that if you use CICSM scheme of OpenFOAM, you see the results which are okay, they're not so bad, but the still interface is wrong. If you use HRIC, the interface is still not so great. But if you use MaxGBCA, keeping everything same, you have a pretty good match. And this is on the Courant number of 0.2. So this is important because we want to create a scheme that can be applied on higher coordination. In fact, the same problem is presented in this paper about isoid vector. Okay, so most people who are using OpenFOAM, they use isoid vector. So this is the paper, and they compare with isoid vector with various schemes in OpenFOAM. And you can see that the isoid vector till the Courant number of 0.5 does very well, while HRIC and CICSM, they all struggle. So this is how isoid vector did. In this paper, I will point out that the results are bad for H-Rig and CICSM because the temporal scheme is first order. If you go to a better temporal scheme, the results will instantly improve. So this figure is a little bit misleading. It makes you think that the results in CICSM and H-Rig are bad because of the scheme, but it's not true. So what could happen if you take care of the temporal term very well and you use max GPCA, then what is possible? Keep in mind that at the moment in isoid vector, based on my communication with the author, Johan, they cannot go above 1. So best they can do if they try is the Courant number of 1. But things change when you use max GPCA. And I present the same result with the Courant number of 1, 2, 3, and 4. Okay. So we, as you can see, the scheme is very, very good. And we try to use validate it for the 3D case. This is the very famous 3D dam break case. And you can see that I run the solver with the Courant number of 10, and still I have a very good match with the experimental result. So the scheme is quite accurate. Now, we do a lot of innovative things. Wildkatze is full of innovation. One of the innovative things is that we blend the wall function with the first two cells. So if you have a prism layer on the wall, and then the next cell, we take the both cells, we solve the turbulent boundary layer, and then we try to blend both the values so that we can get a better estimation for wall shear stress. Now, why do we do that? Because one of the main problem in CFD is that the results are mesh dependent, especially at the wall part. And this mesh dependency shows up when you change the mesh and then suddenly your results are completely changed and you are not accurate. So we are at the mercy of the solver, what it does. You can create as good as mesh as possible, but still. So we want to remove that dependency. So I would point out we are better than others, but Wildkatze is not completely 100% there. So at the moment there is no 100% solution for this problem, but we are better. So to demonstrate this, I show you with a validation case coming from Fluent actually, ANSYS Fluent. This ANSYS Fluent CFX. So this is from their validation case. Everything is same. So what are we doing here? So what is going on is that there is a pipe for which we know the analytical result, and we try to create two meshes, one in the Y plus of 30 to 40, and another is a Y plus around 5. So you many times hear that, okay, you want to get a better and more accurate result, then go to the lower Y plus and you will get good results. But in theory, when you change the mesh, the result should not change and they should be on the analytical result. That will be the ideal case. You change the mesh, result should not change and they should be as close to the analytical. But what happens if you use OpenFOAM in star CCM? And you see that the mesh, when you change the mesh from one Y plus to another, the results change quite a lot. And the highest error in OpenFOAM was around 10%, and the same in star CCM was 10%. While Wildkatze, the highest error is like 3%. Okay, so that is the highest in the second order low RE mesh. And low RE mesh with third order is pretty much on the spot. There is no difference. But we demonstrate that the solver shows much more mesh independence than the other software. So if you use it for your projects, it will show up as you will have more reliable results. To demonstrate that we do better, there is another test case. This is coming from Azure CFD because Jeff was studying on it and then he showed me. So I tried to reproduce the same case with Wildkatze. Okay. So what is going on here? It's very difficult to estimate the profile. And here on the right side, you can see that Azure CFD is doing this calculation and then they are using a commercial package. Now this commercial package is Fluent, okay, as told to me by Jeff, and they are able to get some results. But we do the same case with Wildkatze, and you can see that this point where the profile changes, only higher order solver is able to predict. The second order is doing still better than Fluent and the Azure, but the higher order is the only one who's able to predict this inflection point correctly. So you can see the higher order solver is pretty effective. Now, in 2021, we did participate in auto CFD workshop, and for this case, among the rank solvers, the closest to the experimental result were Wildkatze. So you can see the red dots and the line at the center is the experimental, and we were participant 18, and you can see the most accurate results are still. So, and all the other gray are other softwares. Many of them are OpenForm, Star CCM, Fluent, like this, depending on the participant what they used. Same thing we try to compare with OpenForm for the auto CFD case, and you can see that we still do better than OpenForm for this case. And the OpenForm case is not run by me; we are just taken from the workshop what was submitted, but we are still more reliable results. So you can see that wall function and higher order and everything makes sense. So one of the things that so far you can see that whenever you test it, we come out to be quite accurate. Now, there is a myth that if the software is more stable, it's more inaccurate somehow. So this myth one has to give up, because you can see we are far more stable than any software, but usually we are more accurate. One of the more innovative thing that came out of so far in the research is this split smoother. Now, split smoother is based on polynomial, where we find this alpha. If the alpha is 1, then it become a pure Neumann polynomial. But when the alpha value, we can find out the appropriate alpha value, you can have a very robust AMG solver. So this is what you see. And with the help of this, we are able to get good results for very difficult problems. So this adds into the robustness of the software. So what is coming next? So we are creating the software for the Cartesian mesh. So we are the only one which is a multi-physics framework for Cartesian solver. And we are also developing a multi-CPU solver. So what is Cartesian framework? The Cartesian framework is basically, you have a Cartesian mesh, and given the mesh, the solver will create or mark the regions inside, and then you can solve the general physics on it. So the way it differs from the Cartesian solvers in academics and all is that there you can only solve certain type of physics, not a general multi-physics. So if you want to solve plasma, then you have to write the software again. But in this case, in the same framework, you can add multiple things, multi-phase, etc. Is there any question? Okay, so yeah, please ask.
Yeah, actually, I had a question. I had many questions actually. I thought I would ask towards the end. Is that okay? Or
Okay, you can ask now. We have a lot of time.
okay. No, actually, I was quite interested in you also mentioned about this GPU solver. So what is when like a lot of the literature or what we are seeing is mainly they are either just single phase or two phase. So what is the, so you mentioned that you have a solver which is GPU solver which is multi-physics solver. So
Yes.
so what is different and how does it compare? Because we don't like right now social media or whatever we are seeing in the papers, we don't really understand like what are the difficulties and what really a multi-physics GPU software can do.
So Wildkatze, as I mentioned, that it's a multi-region and multi-phase. So basically, the GPU version has to support that. So I cannot. So for example, if you want to create a very efficient GPU code, then typically you can restrict yourself to some special case, like let's say only have tetrahedral mesh. Then you have 4 phases, and then you can get a very efficient kernel out of it, and then you get a speed up. But in our case, we have to stick to providing a general multiphysics solution. So what we do is that it should be applicable to polyhedral, it should be applicable to two-phase, three-phase, four-phase, like that. You should be able to solve energy, all this multiphysics model. It should be able to support grid-grid intersections, should be able to support the rotation, rigid body motion, etc. So for us, because it's a more general software, we have to give up a little bit on the speed of GPU, but we should be able to provide all sort of things to the user. So if you are a user, you want to do, let's say, a CST where there is a heat source in, and on the fluid side you have multi-phase flows coming up. Maybe the phases are compressible with ideal gas and all. Everything that you can throw at the solver, solver should be able to handle that. That's our idea of multi GPU framework. We support everything, multi-region, multi-phase, all these things. We already been tested for like rotating meshes and all. The solver should be able to support. It should not be bound to just a single type of simulation. If you do that, then you can get a very efficient solution out. But then you can only do one thing. You cannot do more. But the clients who use this software, they want to do a lot of difficult problems. So for us to give up a little bit on GPU speed, and then we can provide. So like for example, here you see this is a two-phase pipe flow. In this case, we have experimental result available for it, and for 15 seconds the water is being flown with varying rate of the flow, and then in the experiment we can see which channel has how much water, what is the height of the water, and we are trying to compare that with the GPU solver. So yeah, that it support everything, polyhedral, something.
I think there is also a question in the chat from Sharik Iqbal. Does the solver work with polyhedral and polyhex core from Fluent?
Yeah, it works on any mesh. Solver works on polyhedral, tetrahedral, any type of meshes. Pretty much you can say. The Cartesian solver will obviously have a Cartesian mesh in the background, but the surface mesh can be anything.
Actually, I had one more question.
Wildkatze will work on anything, any mesh.
Yeah, I had one more question. Actually, at the very beginning, when you were talking about the third order solver, so this is something which I have kept hearing on the various CFD forums, that a lot of the third order muscle scheme, which these commercial solvers are actually calling third order, it is actually not third order. So this is so. Could you talk about that?
So
and how your scheme is different?
I explain what is going on. So when you have a true third order solver, then you have a polyhedral, let's say a finite volume, and in the second order you will take a phase and the phase center. So this is your one integration point for the second order. So you interpolate the variables on that phase center, and then you integrate on the finite volume. And how you interpolate the values to the phase by second order or first order, it also depends on that. But you have only one integration point. And now if you go back, here, so you have, in a typical case, you have one integration point. Now this was a difference with Nishikawa-san's order, third order also. So he interpolated the variable by third order, but have only one integration point for control volume phase. In a true higher order method, you will have more integration points. So typically, if it's a triangular phase, then you will have 3 integration points. Right? And if you say a quad type of phase, then you will have 4 integration points. Now it's costly to integrate on the 3 and the 4. You have to do 3 times the interpolation, 4 times the interpolation. But the difference is very high. You see, the red line is doing the truly higher order way integration. And the third order Nishikawa is doing only one integration point, as he suggested. But it's better than the second order, so maybe he is very happy about the result. But if you compare it with the true third order, then you still lose out. So that's the one thing. And another thing is that in star CCM, the muscle scheme is only for the convection term for momentum. So, but in the case of higher order in Wildkatze, you have every term higher order. That means the pressure gradient higher order, momentum gradient higher order, convection term higher order, pressure gradient term higher order, or the right side. We try to, when we interpolate for the flux, the volumetric flux, for the control volume flux is higher order. So everything is higher order. So exactly how the two higher orders should be, the third order should be, you take more integration point, interpolate on them, and apply the integration that. So this is how, but it's very unstable usually. But in Wildkatze, now that after we spent 2 years trying to do it, we are more stable. The higher order is more stable than even Fluent or Star CCM, second order methods. So you can throw we have tested it on general polyhedral mesh and we get a good result for industrial cases. There are clients who use Wildkatze and only use higher order solver. I know such people.
That was quite interesting, and also the fact that you showed the higher order for TET mesh is actually, it was quite interesting because
yeah, there is a polyhedral result also actually, which are because Nishikawa-san and other person who the Oliver Gucci, they work in higher order method for 20 years now, 10, 20 years. They were once discussing that they are not, higher order is not for polyhedral, but we have a very efficient higher order for polyhedral. So more questions?
yeah, I mean, I also wanted to ask whether this like this higher order goes well with the compressive sorry, the multi-phase, or does it create oscillations? I mean, is that available, damping out those oscillations?
Our higher order is not creating oscillations, but usually the multi-phase calculations we don't suggest. They are usually, because in the multi-phase calculations, usually the phase is very important and this accuracy does not really play that much. But in Wildkatze, you can use higher order in that also because it only had 30-40%. But typically people don't use it. I think you can use one case where, let's say, one of the phase is compressible, or both of them are compressible, but there is a sharp interface, but you are doing acoustics and the waves are passing through it. Then it makes sense to use higher order. If you are doing acoustics of the water, because there was a client who did when there is a pipe and the water is leaking out, and he is calculating the sound, how the sound wave is going in the pipe, so in the water we are calculating. So maybe there it makes sense to use for acoustics. Yes. So if you have multi-phase acoustics you are doing, then it makes sense. More? Because my presentation is pretty much there now about it.
Yeah, so Ahmed, there's a question here.
Yeah, I know what the question is about. So there are two things. Okay, one, you have a very difficult pressure gradient, the solver, and the other solvers get unstable. That's one aspect of this question. That type of problem we don't have. If you have a calculation which is extremely difficult to converge in other softwares, you will be surprised. You set up and it will run in one go. Actually, from 2020 or 2021, I have had only 2 cases that have diverged. And one of them diverged because of radiation. And one diverged because the Courant number was hitting like 300 in the particle. So that only 2 cases have been diverged so far. Another question, another aspect of this adverse pressure gradient is to do with wall boundary condition here. And usually the boundary conditions, the wall functions are not sensitive to adverse pressure. But in this case, actually, when you are solving this non-uniform TBLE, that time there is a pressure gradient given to it. So you have to create a one-dimensional Navier-Stokes equation for here and solve. And there the pressure gradient is given from it. So we take the pressure gradient from the cell center here, and they are given to it. So it's kind of like sensitive to it, but maybe not that sensitive, but yes, it's better than the other software. More questions?
Yeah, actually, the comparison which you showed with the with auto, I'm sorry, I forgot the.
Auto CFD, yes.
Yes, yes. So, I couldn't really understand these. This open form you have shown as a straight line, and here.
Yeah,
So
that's
I'm
because
sorry, I
I
couldn't
only
understand.
have the one result given from the open form workshop. So they report it, this is the CD they got from open form. So they only report one value. So I don't have
Okay,
a
okay,
iteration
okay,
graph for it.
okay, okay,
So that's why I plotted the one straight line, like just like an experiment here.
okay, okay, okay.
So for this case, the people who participated in workshop, they have presented their results. So it's not run by me. So basically, what it was presented, and they presented this CD value. So that,
So
and
also.
everything else is same. Basically, K omega model they use, we also use it. So everything is same, just the two different solvers.
Okay. Yeah, the main question which I had, like at the very beginning, actually, when you mentioned why Wildkatze and how it is different from the commercial code, like in a very practical sense, um, could you tell people like which could you talk about some test problems probably in which Fluent is simply not able to solve it, or open form at least we can understand that it is not stable, but Fluent of course.
I can tell you.
Yeah.
So what happens is there are commercial code are usually able to solve it, but there are cases where people they are not able to solve. That one of the case was one university student from Sweden, and their group was doing where they have ice, and the ice is getting melted on a rail track. Now, when the ice will get melted, there is a air that is coming, and the air will blow the ice. Now, all the solvers they do this solidification melting by increasing the viscosity. So if you increase the viscosity, then the forces on them are not correct, and so that means they cannot move this ice due to the air. So if the air is blowing and the ice, so their group was struggling for it with like 2.5 years or something. They tried every software. They tried Fluent, they tried Star CCM, console, everything, open form. They were not able to do that. So, for example, then he told me that, can you do that? And then for the first time, they were able to see that. And maybe there might be animation for this type of test problem, if I can find. Is there animation here? Yeah. So this is a typical example of that. You see. So there is a ice that is getting melted. This is the first test problem that we showed. And then it's melting to the water, and the air is also blowing. But in any other solver, it does not work like that. It does not, ice does not move at all with the air. You see, that was one question. Another calculation that could be very difficult, was not able to do, is this one. This is a vacuum pump. So there is a vacuum type situation getting created, and this is a liquid ring pump. You see the water outside, it's rotating, it will create a ring. Now, because the vacuum type of situation happens, CFX is the only software that was stable for the client, and that too sometimes diverges. Fluent and Star CCM and OpenFOAM have no chance with this problem. They cannot run it even few iterations. So that was another problem. Then there was a problem coming from Star CCM where they want to do circuit breaker in vacuum, and the pressure is very low, like 10 to power minus 5 Pascal or so. And after 6 months of trying with Star CCM, it was not stable at all because pressure is too low. So we had no problem running with Wildkatze. There was this problem from a client where they use Star CCM, but you see this structure where this is going under. Experiments show this structure, and client tells that they're never able to reproduce with Star CCM. But the very first go with Wildkatze, they're able to reproduce. Another calculation is, I warn you about the sound because I'm going to play something that will have a lot of sound. And here you see, there are 1,000 nozzles in it. And the water will go and it will create like that. And the same thing is simulated here, you see, with the 1,000 nozzles. This is not a difficult, I think you can do it, but here it's far more efficient to do it with concept, because it can take a larger delta. This was one thing that was pretty much difficult to even mesh, because it was paper cut, thin pipes inside. So there were a lot of problems which are difficult to do with concept. This is one problem. For example, here you see compressed nitrogen is coming out and then becoming vapor. So it's a very high speed flow. So there are many difficult problems. But this is actually a Cartesian solver. Probably you have seen this animation. But this is a Cartesian solver with the VON. Yeah, so there are a lot of projects where client not able to do it. We get a lot of projects. We only get the projects where client, or I would not say only, but most 80% of them, because everyone has their software that they use. They typically don't want to change. But when the situation is that you cannot do with any other software, then this is. Yeah, so I go a little further and quickly wrap up what this part. So the design and concept of Wildkatze, which you see that make it much more advanced than other thing, is that you have a mesh. Yeah, what was the question, Shari?
Yeah, hi. So thanks for the details. I have a couple of questions. One thing is, we are now seeing that around the world there is a lot of focus on electrochemical applications at the industrial level, be it battery, be it fuel cells. So, do we have those sort of solvers capabilities within Wildkatze? This is the first. And are there any comparisons which you have in your slides regarding the high performance computing capabilities which are present in, or what sort of comparison between Wildkatze and other commercial or open source ports regarding the speed of the solution? Yeah.
HPC only I know from one independent source that is try to do, because I will be biased if I say, but I can tell you what one of the client here in Stuttgart, they compare Wildkatze with CCM, and they took a case which was 3 million cell or roughly 4 million cell, and they go from on their machine, okay, so to take it, so they go from 40 processor to 80 processor, and ideally the speed up should be 2 times, correct? So if you double the processor, so they go from, and the star CCM's speed up was 1.7, and Wildkatze's speed up was 1.59 or 1.6. So we were inferior to star CCM there, but not so far off that. But I was surprised personally, because on my machine, my personal machine that I'm using at the moment, I do not get on this particular case scaling above 12. So it depends on the hardware. I mean, on that case, he is able to get 1.6 going from 40 to 80 processor. That for me. So it's typically, you can say, a star CCM type performance, but slightly inferior. Okay. So. And about the chemical part, solver has reactions, etc. on there. Combustion is also there. Now, we are doing projects where the client need to have reactions in the phases. So electrochemical would be similar category, but we have a reactor calculation where there is a powder which going through a reaction, and then there is a client who is doing immiscible liquid. There are two liquids which are going with each other, and they will transfer the heat to each other. And one of them will go through the reactions. So the combustion who has the chemical reaction system, now it will be provided to phases also. And one student in France also wanted, he's doing a polymer which is going through reaction. So within 1 week or 2 weeks, I have to actually provide the combustion system, reaction system to general phase, so that even the user should be able to call it. So imagine that you do the user coding, and the solver has a reaction system, and you say, okay, for this reaction system, can you step it up by delta T and give me the species and temperature? So that will be available to user coding, and the models will anyway have. there is a reactive polymer model already. If you have a, let's say, resin, etc., which is going through the curing type of reaction and getting solidified, that already exists. But for a general chemical reaction that we provide a chemical mechanism, only at the moment combustion is using it. So it should be actually provided to the phases and the user, but that is still there. I mean, I have to provide it for my own projects, which are ongoing, but so that will be helpful. Yeah, more questions.
Thank you.
Yeah, so let me finalize this part. So the concept of Wildkatze is that you have a mesh which has multiple regions, and you can just create a set of them. Let's say any set you can create, any 2-3 regions you choose, you create a set, and then you as a user define the phases. You can define flow, air, water, other resin, whatever polymer phase, and then you can create a set and create a physics model on it. So basically that allows you a very high level of flexibility. So for example, if you take star cesium, you have to only define a continua, and then in the continua only you can do it. But here you can create any set of the phases and they can talk with each other without any problem. So it's already very, very flexible compared to other stuff. Now the same thing you can do in OpenFOAM, but it will be nightmare because you want to create a set of the regions, another set of the regions, and then, like for example, you're doing CST, and the CST you do, let's say, all the regions. Then the flow you do on certain region. You can have a chemical reaction going on in certain phases, so that you cannot do. But here it's part of the framework. So the solver will take care of everything, like how to provide you memory, how to access, give you linear system solving, and also it's designed to be a multi-region and multi-phase. Grid intersections, everything the solver takes care. You don't have to really worry about it. Like in OpenFOAM, you get stuck, then you are asking in the forum, how do I do this? In fact, there are cases I see in the forum where people are asking, which are like 3 hours job in the solver, but they are struggling for 2 years. And now this thing works, then other thing does not work. So, but here this is the idea, and that allows a very, very high level of flexibility and advancement. Like boundary model, for example, you don't have this concept. Maybe in OpenFOAM you have a finite area, and to some extent in star cesium, thin film, etc. But here you can create a general physics model on the boundary and solve it. So if you want to solve, and we can increase the features by a feature submodel. That means you have a feature that is not generally used, but for some applications it's needed, so client can just simply add it. And also another thing that we have added, which is you will see in action now, is the automatic setup. So you can just give a command line to set up. So if you are a user who knows nothing about the software, never used it, but it's somehow installed and you have a mesh file, you can still set up and run. So for example, this is setting up from the configuration, but I will do in the next session, set up automatically and run it. So you given a mesh and it can automatically set up everything for you, the basic setup, then you can change it. Or you can do advanced setup completely from the scratch, but 90% of the cases, 95% of the cases, everything you can automatically set up. So you given a mesh, one line of command, and the basic setup is there. So if you are an OpenFOAM user, you can see that creating the folders, many files and all, it's not going to happen here. You have a mesh file, immediately sets up. Even in this case, I'm setting up and I'm also iterating and exporting the result. You see -LC, iterate to 100, -LC, export results. It's basically setting up the whole thing, running it, and exporting the result. And this is doing from the scratch. And it's a complicated shell queue. We will have this as an example later on. But here you have like 4 or 5 regions and multiple interfaces. And everything is done just in one command. Once you create a configuration file, even if you change the mesh, you can again and again set up every time. So, yeah, so this is basically, this conclude. You can download the Wildkatze from here, and we can provide you a demo license file to try. And don't worry, if you are an individual, you can always use the software. And I have uploaded the new current version here. You can download and use it. Or when it's available on DiceHub, it's now kind of available. You can use there also. Okay. So in the second half, we try to see how to use it, and we discuss edit. That is a very lightweight session. You have a question, you can keep asking me.
Yes, thanks, Arjuna. It was really very inspiring. So, just in 1 minute, if you could tell us, like you developed this from scratch yourself, or there are also other people involved, or how did you manage this over 10 years? I mean, you said from
Yeah, so
2015.
I develop everything from the scratch, and I have philosophy of everything in-house. That means I don't want to use external libraries, because then deployment is a problem. So I write everything. So first 2.5 years, I was working every day I'm still working every day, but now on Wildkatze only on the weekend. But first few years till 2023, I worked on it daily. So like 6-7 years non-stop programming. It's quite big code. Wildkatze at the moment would be like 1.5 million line of code, and the total code will be like 3 million line with other softwares, GPU. So it's a quite big code. It's very advanced also, extremely advanced. More you will use it, and then you'll see how advanced it is. Everything that you think, okay, it's how I can do in this software, it will come easy in it. And even more you become expert in it, then you can do far advanced things that you will be actually even not dream about doing in other softwares.
This is really, really very inspiring. uh, so,
Yeah, for us, we developed it like, I mean, we should use it also. Surprisingly, not many people know, to be little bit of my fault actually.
no, so I think we'll break now for 5 minutes, and after
Yeah,
5 minutes we can resume again with the
then we
demonstration.
see the use of the,
Yes, yes.
okay.
So guys, the next session is actually in another link. Both the links were. So guys, the next session is in another link. Actually, both the links are sent to you. So the workshop, so you can join the workshop by joining this link. So this particular link you can close now. Thank you.